In this video, I would like to explore a more qualitative relationship between electric field and potential. So let's start with just a point charge. And for the case of a point charge, we know that the potential is just going to be given by kq over r. So if I take a point charge and let's say it's positive, and I can draw the electric field for this case. We've done that before. So I'll just do a bunch of electric field lines, evenly spaced, pointing away from this positive charge. That's one way to represent what's going on near the charge. But we could also represent the potential. Okay, so looking at the formula, I can see that at a given r, so some distance from that charge, the potential will have some value. I don't know what the value is, but some value. I could calculate it if I have the charge and the distance. Okay, so let's just pick a value for r. And if I draw a circle at that radius, everywhere along that circle will have the same value for the potential, because it's all at the same distance from the charge. Okay, so let's say that's, I don't know, 10 volts. And if I go half as far from the charge, then according to the formula, that will give me twice the potential. So this would be 20 volts. Okay, and if I went twice as far out from where that 10 is, then I should be at a 5 volt potential at that spot. Okay, and I could go in between and get in between values, and I could keep going closer and closer to the charge and get higher and higher values. But this is another way we can represent what's going on. We can map out places where the potential takes on certain values. Okay, so we call these equipotentials because they're places where the potential is equal. So it's a relatively simple way that we can represent what the potential looks like in some region of space. Okay, so a way to think about what this represents is we can think of the potential as being like a hill. So we can think of this as potential is like the elevation. So I can draw this same picture, but in sort of a three-dimensional case. Oops, let me not do it that way. So if I draw something kind of like this, the potentials, the equipotentials, are going to be kind of like this. We've got this sort of three-dimensional sort of traffic cone shape that represents the same thing. So the positive charge is in the middle, and these different heights correspond to maybe 20 volts and 10 volts and 5 volts, or what have you. And then trying to make sense of what the electric field looks like here, well, the electric field kind of points outward radially from the center. So it's essentially pointing downhill everywhere along this hill, if you want to think of it as a hill. So V is like the elevation, and E points downhill. All right. So to do another example like this, what if we had a negative charge instead of a positive charge? So I could have essentially the electric field lines pointing inward, and the potential gets lower and lower as you get closer to the charge. Notice that you'll end up with negative potentials if you have a negative charge. Okay, so here the electric field is still pointing down into this cone. And we can imagine that this is sort of a well rather than a mountain, if you want to think about it that way. And so this can be a really nice way for us to visualize what's going on in terms of the potential in some region of space. We can think of it as being related to the electric field in this sort of intuitive way. Okay, so it can be helpful to relate this to our experience with ordinary hills. So let me sketch out a hill like this. And we're going to imagine that this is a real physical hill. And if you imagine that you are standing somewhere on this hill, okay, there's you. As you look around you, what you will find is that there's some direction where you can walk along this hill without the elevation changing. So there's some perfectly horizontal line that you can follow without going uphill or downhill. And that would be true at any point on the hill. So there's some sort of line of constant elevation at each of these different spots. Okay. If you look at that line and say you keep looking around the hill, what you'll find is that there's some direction perpendicular to that that points most steeply downhill. And opposite it, you can go most steeply uphill. Okay, and those two lines, the one that points most steeply uphill and the one that is horizontal, those are perpendicular to each other. Okay, so there's a 90-degree angle between the direction you can walk to not go up or downhill at all and the way to go directly downhill. Those are not free to be any relationship. They have to be perpendicular to each other. And that will be true anywhere along the hill. Okay, no matter where you consider, these lines are going to be perpendicular wherever they cross. Okay. And that's just a property actually of math. That's not even detail about hills. That's true for any sort of relationship like this. If you have the direction of most rapid change and the direction of no change, those are always going to be perpendicular to each other. So this is going to be true for electric fields and potentials, just like it's true for constant elevation lines and the line that points directly downhill at each spot. So in maps of hills, one way that we represent them is with what we call a contour map. So for instance, we can have some sort of map that kind of looks like this, and then maybe inside there's something kind of like this, and then maybe another one here. And so maybe what this map represents is that, okay, this one is an elevation of 100 meters, and this one is 110 meters. Maybe this one's 120 meters, this one's 120 meters, and this one's 130 meters. Okay, so we can map out lines that are a constant elevation, which again, that's called a contour map when it is mapping out the literal ground. And we could also, on that map, imagine that we dropped some water, and we could say, okay, if I spill some water here, it's going to want to go directly downhill. So kind of like this. But if I drop some water over here, then it's going to want to go directly downhill, kind of like this. And maybe over here, it's going to want to go kind of like that. And so you could just imagine that you are mapping these out, and you could pick some different locations. Maybe here it's going to go like this, maybe over here like that, and so you just map out a bunch of different paths that the water can follow to go directly downhill. And what you can see is that this looks exactly like electric field lines and equipotentials. And the exact same relationships are true between them. So the field lines and equipotentials cross perpendicular to each other. Also, where electric field lines are close together, the electric field is strong. We've seen that as a rule before. But that same rule also works for equipotentials. So if I look at a place where the elevation is changing rapidly like this, or I look at some other place where the elevation is changing slowly like this, well, if it takes a long distance for the elevation to change a little bit, then it's not very steep. If it is if the elevation is changing rapidly in a small region, then it's very steep. Okay, so where equipotentials are close together, we also have a strong electric field. So close electric field lines imply a strong field, and close equipotentials also imply a strong field. Right? If you imagine that there's some region where the height of the hill is not changing at all, then that means that the derivative of that height is really small. Okay, so the hill analogy is really nice because it gives us a way to visualize what an electric field and a potential might look like in a region of space. But another thing that I want you to see is that these are two different ways of representing the same structure. So if I imagine this electric charge as having this invisible agent around it that's going to cause the interactions with all the other charges, well, the electric field is one way to think about it, but the potential is a different way to think about it. Now, don't get me wrong, these are two different quantities. One's a vector, one's a scalar. They can be big or small in various combinations. So don't get them mixed up. They are two separate concepts, but they are closely related. So they're two different ways to represent this invisible structure. Just like I can represent a hill by saying, okay, here's a map of arrows where I'm looking downhill at each point on the hill. Or I could say, all right, here is the contour map of elevations for the hill.